Let us move on now to a new property which we call stability. While causality and memory both referred to the regions of time over which the input signal provided information for computation of the output signal at a particular point, stability has nothing to do really with the time axis as such. Stability has more to do with the values of the signals, with the range of the signal rather than the domain of the signal. So, let us put this down. So, what is stability? If we consider a particular system, as we said, it can be understood as a lookup table. For every kind of signal that we apply to the input, there is always some output signal that exists. However, if we go back to our discussion about the preliminary properties of signals, we will recall the definition of finiteness and boundedness of signals. So, recall boundedness was the property of a signal that was present if the absolute value of the signal never exceeded at any point of time a certain fixed value called the bound. So, if that is the definition of a bounded signal, then if we take the world of all possible signals, we can extract from them the subset that consists only of bounded signals. So, the set of bounded signals is a subset of the set of all signals. If this is the set of all signals x, then inside this is considered this subset of, I will call this B of bounded signals. B is the set of all bounded input signals. Now, let us go to the range set which we used to call Y. It will be recalled that Y is the same set of signals as X, except that we draw it separately to indicate that it is the set of output signals, though in every other way they are indistinguishable from input signals, they are both signals. Now, even here there will be the same set subset B. I will not give it any other name, maybe I can call the first set B x and I can call this B capital Y, B subscripted by capital Y. So, these are also bounded signals in the output signal space. Now, a stable system is one about which the following can be stated. For every signal that is bounded in the input, the corresponding output is also a bounded signal. Let us put that down. For every input bounded signal, for every bounded input signal, the corresponding output y t is also bounded when the system is stable. In short, a stable system has this property about its lookup table or about its map that it implements on the signal space, that every member inside this set is mapped to some member of this set over here. What is not allowed is to map an input signal which is bounded to some output here which is not bounded. The dotted line that I have just drawn is an instance of a signal of a map that cannot be allowed for a stable system. For a stable system, only these solid lines will represent associations between inputs and outputs. Every bounded input signal must be associated with a bounded output signal. What restrictions does the definition place upon input signals which are not bounded? After all, the input signal space had this subset which we called Bx, and the entire space was this. What about all the signals in this region? What should a stable system satisfy with regard to signals in this outer region? The answer is that there is no restriction on them. They can do what they like. The response due to an unbounded signal, that is a signal in the outer shaded region, can still be a bounded signal. Thus, for example, if this is the output space and this is the By set, then it is quite legitimate for a stable system to take a signal in the unbounded subset and map it to a signal in the bounded subset. There is no problem there. It can take an unbounded signal and produce an output that is a bounded signal. Even if it does so, it is still considered a stable system if for all the bounded signals over here, the outputs, corresponding outputs are bounded. However, even if an unbounded signal, that is a signal in the outer region, goes to some other signal in the outer region over here, even so this system is stable if the signals in Bx are mapped to By. In short, therefore, we may say the following, that for a stable system, every input x t in Bx must result in a stable must result in a bounded output. Y t in By. Just to clarify further, let us also talk about what is supposed to happen to signals not in Bx. For signals for input signals, x t not in Bx no restriction exists regarding the output. The output for a signal x t not in B x could be in B y or may not be in B y, it does not matter for us. So, that is a rather dry, if you like, rather formal definition of stability. Let us try to understand more clearly what this means in real life. If I place this pen at this point on the table and displace it slightly with my hand, it moves only slightly, corresponding to the amount of force I apply, it will move from place to place. But if I place it on a convex surface, there is no convex surface here to demonstrate, except perhaps this slant of the desk. If I place it somewhere here and just even tilt it slightly, it will slide all the way off. The response, in short, would be disproportionate to the input. Even if the input is bounded, even if the input disturbance applied to the system is bounded, the output disturbance that is caused is unbounded. Such a system would be called unstable. The system which maps the input disturbance to the output disturbance would be unstable if the output is unbounded when the input is bounded. So, there are lots of instances in real life of stable systems. For example, an amplifier, a normal amplifier, properly designed amplifier of sound signals is stable. If you apply an input signal which has some bound on it, it only gets scaled up in magnitude or amplitude by a certain factor which is the gain of the amplifier, and so the output will be a signal which has wider variations, but still is bounded. As long as the input is bounded, the output is bounded, and if the input is not bounded, then as we just followed from our definition, there is no restriction on the output. If the input is unbounded, the output is free to be unbounded. We will not blame the system and call it unstable if it produces an unbounded output when the input is unbounded. It is only important to produce a bounded output when the input is bounded. So, there are many systems where things are unstable also. For example, if you take an object such as this and place it vertically, I do not dare to do it because it will fall down immediately, and if I had let go of it and even applied the slightest force at the top, irrespective of the force I apply being extremely small, the response will be very large. The system will cause the pen to fall. This is an unbounded system once again. So, an unstable system once again. So, stability is a very natural physical property which we encounter in all kinds of situations, mechanical situations, electrical situations, all kinds of situations. In fact, the property of stability as we have defined it is considered to be the simplest form of stability. It is called bounded input, bounded output stability. Let us now start taking a few closed form examples and see if we can understand what we mean in practice by this definition of stability, whether we can characterize a system's property as either stable or not stable by looking at the closed form description of the system, how it maps the inputs to the outputs. Let us take examples. One, let y t be equal to say 4 x t. Is this system stable or unstable? This system is completely defined, because for every input x t that we can substitute on the right side of this equation, there will be some y t that will result automatically naturally, and so this system is going to be stable anyway. This system is well defined anyway. The question is whether it is stable. In order to answer this question, the procedure is as follows: set a bound for the input, because we are concerned only with bounded input signals. That is the only part that is of concern when we consider the property of stability, bounded input signals. So, set a bound for the input. Call it say Bx. Bx is a number. Bx is a number whose value is never exceeded by xt or by the absolute value of xt for any time instant t. In short, we can say that xt, absolute value of xt, is less than equal to Bx for all time. Fine. So, this is a bounded input signal. Now, if the system is stable, it ought to produce as an output signal which is also stable. In some sense, the bound is the worst case value of the input signal x t, because x t can be less than the bound, or the absolute value of x t can be less than the bound, but never more than the bound. Hence, suppose we apply a signal x t equal to the bound, then what would be the output? We can find the answer to that by looking at the definition of the system, namely this y t equals 4 x t. If we look at that, then we find that if we applied Bx as the input, then we would get y t equals 4 Bx. Now, if Bx is a finite number that bounds x t, bounds the absolute value of x t for all time, then clearly 4 Bx is also finite. If Bx is a finite number, that is, if Bx is not infinity, if Bx is less than infinity, then 4 Bx is also less than infinity. So long as it is less than infinity, this number 4 Bx can be called a bound for y t. So, we can call this number By and say that mod y t is never greater than By for all time. This shows that the output is also bounded. Note the crucial point of this argument. The crucial point of the argument is that once we have set a bound Bx for x t and applied the system on the extreme case of the input signal, namely Bx, that is a DC signal of value equal to Bx for all time, then calculate the output. The output is 4 times Bx. The crux of the argument is to show that when Bx is finite, 4 times Bx is also finite, and hence y t is also a bounded signal, because 4 Bx acts as a bound for y t whenever Bx acts as a bound for x t. So, when the input is bounded, the output also has a bound equal to 4 Bx, that we have called By. More examples. Let us take y t equal to x squared t. This seems a little more doubtful, because as we all know, the square of a signal can be very large even when the signal is small. 100 squared is 10,000, 1000 squared is 1,000,000. So, are we talking about an unstable system when we make this definition? The answer is no, and the way we obtain the answer is the same as before. We are concerned only with bounded input signals. So, let us say let Bx be a bound for xt, that is Bx is greater than or equal to mod xt for all time. Okay. This is just an abbreviation for writing minus infinity less than t less than infinity. So, Bx is a bound for xt. We have chosen only a bounded input signal. Okay. Now, when we have a bounded input signal, what can we do with it? We consider the extreme case of the input signal, that is when xt achieves the bound xt equal to Bx or mod xt equal to Bx, in which case Yt would be equal to Bx squared. Now, coming to the crux once again, what can we say about Yt now? If Bx is a finite number, a number less than infinity, then Bx squared is liable to be very large, particularly when Bx is greater than 1, or particularly when Bx is greater than 1, Bx squared will be much larger. If Bx is between 0 and 1, then of course Bx squared will be smaller than Bx, but in general we can say without loss of credibility that Bx squared is also certainly finite if Bx is finite. If Bx is finite, then Bx squared is also finite, and that is the crux of the argument, which says that Bx squared can be designated as a bound for y, and hence Yt is also bounded. Yt is also bounded. So, if the output of a system is the square of the input signal, while the output can get very large even though the input is not large, that does not in any way make the system unstable, because as long as the input is finite at every instant of time and has a bound Bx, the output will also have a bound which is the square of the bound of the input. So, this is also a bounded system. 3. Let us go in the same direction that we have gone. First, we had a linearly scaled version of xt, we had Yt equal to 4 xt, now we have Yt equal to xt squared. Let us try to see if we can make a system unstable by making Yt an even faster growing function of xt. Suppose Yt equals 2 to the power xt. Is this an unstable system? Going by past experience, we should not be deceived into thinking that this system is dangerously unstable, because it actually is again not unstable. If Bx is a bound for y for x, suppose Bx is greater than equal to xt for all t, that is Bx is a bound for x, then can we find a bound for y? As usual, we ask the same question, can we find a bound for y? And the answer is again yes, because when xt achieves its bound of Bx, Yt will be equal to two to the power Bx. Now, if Bx is not infinite, if Bx is a finite number, 2 to the Bx is liable to be extremely large, but it will still be finite, and that is the important point. Exponentiating Bx is not making it infinite. Exponentiation or raising it to a power or scaling it by a scale factor, all these things can never make a finite number into an infinite number. It will keep a finite number as a finite number, and therefore, 2 to the bx can be designated as a bound for y, because 2 to the bx is also finite whenever bx is finite. It is of course quite possible that for a particular bx, 2 to the bx is much larger than bx, but largeness is not our problem, infinity is the only problem, and therefore, by is certainly greater than equal to mod yt for all t. So, again yt is bounded. So, again and again we have found that for 3 successive examples x t was bounded, and for every instance of a bounded x t the output was also bounded. Let us at last turn to some example of a signal of a system where the output need not be bounded, even though the input is bounded. What about yt equals tan x t, the tangent trigonometric function? What if yt equals tan x t? Tan x t is not a safe function. There can be an instance where x t is a finite bounded signal, not just finite, a bounded signal, but yt can become unbounded. It is very easy to see when this happens. Let us now take a fresh example, this time for the first time an unstable system. 4. Let yt be defined as tan x t. The trigonometric tangent function, if you recall the graph of this function, is one where for even finite values of the argument, the value of the function goes to infinity. Let me just plot on the side here some instances of the tan function. So, if this is pi by 2 and this is minus pi by 2, then in this region the tan function shoots towards infinity starting from very innocent values and goes this way, and towards negative angles it goes this way. It goes towards minus infinity near minus pi by 2 and towards plus infinity at plus pi by 2. Now, beyond this it repeats itself, it has a periodicity of pi. So, this is how the tangent function looks. Now, you clearly see here that for x the value of the input equal to pi by 2, the output is infinite. In short then, if we consider an input signal x t over here which achieves a value close to pi by 2, the output will start increasing without limit. The output will be unbounded even when the input is bounded. For example, if I take a signal such as x t equals 2 sin t, the sine function is bounded from minus 1 to 1, the 2 sin t function will be bounded from minus 2 to 2. So, about this signal we can say that Bx equals 2, because mod x t never exceeds 2. So, input is clearly a bounded function, but pi by 2 is approximately equal to (1.57 dot dot, it goes on forever. So, this is pi by 2 and it is clearly less than the maximum value achieved by x t. Whenever x t goes through this value pi by 2, which it will repeatedly do because it is a periodic signal, at every one of those instants y t will tend to infinity. This is an instance of a system where a bounded input will yield a signal at the output which is not bounded. What happens if we proceed to examine the stability of this system along the same lines that we have applied so far? Let Bx be a bound for x t, we already have a Bx, Bx equal to 2 is a possible bound, even Bx equal to 1.8 if we had used a different x t would have been fine. For this particular x t, of course, we can any number greater than 2 is also a bound on x t. Now, if we let x t cross its bound, in this case the bound is 2, the extreme value of x t is not of danger to us, because at x t equal to 2 y t will be finite, that is not the problem. But for values even within the bound, namely at a value like 1.57, this output signal will tend to infinity. So, if we say that y t equals tan x t and substitute the bound for x t, that is we write tan B x. Does this give us an indication of the output being unbounded? It does, because the tangent function is not a bounded function, as can be seen from the graph drawn on the side. The tangent function is not a bounded function, and for a function which is of this sort, even though the argument of the tangent function is bounded, the value of the tangent function need not be bounded. So, y t is not bounded. That is to say, the system is not stable. One more example, also an unbounded system. Unbounded systems, or rather an unstable system, can arise if y t is given as 1 by x t. This is also an unstable system. Why so? Because 1 by x, which is the function which relates y t to x t, is again not a bounded function. Recall what 1 by x looks like. We let us make a graph in the same place on this paper. This is what 1 by x looks like. Even when, especially when x takes a very innocent value like x equal to 0, 1 by x will tend to infinity. Thus, even if we set x t equal to 0 or x t equal to cos t, any of these input functions, they are all bounded, but the output would not be bounded if y t equals 1 by x t. And clearly that can be seen if you set x t equal to the bound and say y t equals 1 by b x. Now, even when b x is a finite number, 1 by b x need not be a finite number, because for b x equal to 0, as seen from the graph, the value of y t that will arise is infinity. So, here again y t will not be bounded. even when x t is bounded. So, this is also an unstable system. Thus, the closed form expression of the system gives us information indirectly about the stability of a system. If the system is described by something like y t equals 1 by x t or y t equals tan x t, then we have on our hands an unstable system. Now, the funny thing is that 1 by x t and tan x t probably look more innocent than functions that we discussed in the earlier examples, such as y t equals 4 x t. That sounded very dubious because y t was an amplified version of x t. This would give at first glance an impression that the y t is going to be very large, even though x t is not large. But that kind of largeness is not going to scare us with regard to the stability of the system, nor the subsequent examples such as y t equal to x squared t. Though we were squaring the input signal to obtain the output signal, and therefore often likely to get a larger output signal, a signal with greater amplitude than the input signal, still this system is perfectly stable. So, also the third example, exponentiation. The output could be much larger than the input, but still this system is bounded. What in fact is not bounded is a system such as this or this. All these are unbounded systems, are unstable systems, sorry. So, stability is this property of maintaining boundedness of signals. That is to say, if the input signals are bounded and that boundedness property is maintained in the output signal, then we will say that the system is stable. What can we say about real life systems? We could say, for example, about real life systems that they were all causal. So, with regard to the property of causality, it was clear that real life systems were always causal. What can we say about real life systems with regard to stability? There is no clear statement we can make, because in the real world we have instances of systems which are stable, instances of systems which are not stable. All kinds are available. We move on to another important definition, another property of systems which we call linearity. Linearity has again got something to do with the range of a signal, is concerned with the range of a signal. What is linearity? Linearity has something to do with proportionality of y t with respect to x t. It can also be said to support superposition or to relate it to superposition of inputs yields a superposition of the outputs. Let us discuss this in terms of a few examples. Let us make a definition first. We will say that a system is linear if it satisfies simultaneously two distinct properties. The first is called homogeneity. This is the property that I had earlier called the proportionality of y t to x t. If the system takes a certain signal x t to an output y t, then the system must necessarily take k times x t, which is a different signal. It is the signal x t multiplied by the constant number k to the signal which is k times y t. So, if x t goes to y t, then k times x t has to go to k times y t. This makes a system homogeneous. The second property is called additivity. The property of additivity refers to superposition of inputs and outputs. What we say over here is this: if, as we said here, if x t goes to y t, then k x t has to go to k y t for all k. That is what we had for homogeneity. What we will say over here is this: if x t goes to y t and say x prime t goes to y prime t, where x t and x prime t are two different signals and their corresponding outputs produced by the system in hand are y t and y prime t, then a system which is linear, which is additive to be more particular, must take x t plus x prime t. Remember that when we add two signals, the result is still a signal. In fact, when you add two signals, then the sum of their respective bounds is a bound for the overall signal. This is a property. Therefore, when you add two bounded signals, you can be sure that the sum is also a bounded signal. This is by the side. Going to our definition of additivity, if x t goes to x y t and x prime t goes to y prime t, then if you applied the input x t plus x prime t, which is a new signal, the output must necessarily be y t plus y prime t. Whenever this is the case for all x t and x prime t, and homogeneity holds for all values of k and for all x t, then we will say that the system is both additive and homogeneous. that is, we will in short say that an additive and homogeneous system is simply said to be linear. We will say that it is linear. The best way to understand linearity also is by invoking a lot of examples. Let us do that, starting with a very simple example. What if y t equals x t? Is this a linear system? To answer that, we will have to test whether this system given by this closed form definition satisfies homogeneity and satisfies additivity. If the answer is yes to both these questions, then and only then can we say that the system is linear. So, let us test it for homogeneity. If y t equals x t, then let me define a new signal k x t. The definition of the system simply says that whatever the input is, the output is the same, neither larger nor lesser, neither delayed nor advanced in time, it is just the same signal. So, if I apply x prime t to the input, then y t must be equal to x prime t, the output must be equal to k x t, or coming to this definition it should be equal to k y t. So, if you applied k x t to the system, then you should get k y t as the output. So, the system is homogeneous, very straightforward. What if whether the system is additive is what we will have to look at next, whether the system is additive. So, let x 1 t go to y 1 t, which according to our definition equals x 1 t, then x 2 t let it go to y 2 t, which by the definition of the system will be equal to x 2 t. Then when x 1 t plus x 2 t is applied, as a new input, the output will simply be the same as the input, as we have been told. It will be equal yield y 1 t plus y 2 t equal to x 1 t plus x 2 t. Since y 1 t plus y 2 t is the output corresponding to the sum of the inputs, we again see that the sum of the outputs results in the sum of the inputs results in the sum of the outputs. So, the system is additive. So, the system has already been shown to be homogeneous also. And jointly therefore, we can declare this system to be linear. The system is linear. Second example, here is a system which gives y t to be equal to x of t plus 1, that is, it you can clearly see that this is a non causal system, because to determine y at t equal to 0, it requires x at t at the input at 1. So, clearly the system is not a causal system, but that is not our concern here. We are busy in this case with studying linearity. Is this system homogeneous? If y t equals x t minus 1, and if I apply k times x t as the input, the output will correspondingly be k times x t plus 1, which is equal to k times y t. So, k x t has yielded k y t. That means the system is stable, the system is homogeneous. Now, let us see what happens if we test for superposition, that is, if we test for additivity. Suppose x 1 t yields y 1 t, x 2 t yields y 2 t, and we apply the inputs x 1 t plus x 2 t. So, let us see what happens when you apply x 1 t plus x 2 t. For this new signal, what will be the output? The output will be x 1 t plus 1 plus x 2 t plus 1, which is equal to y 1 t plus y 2 t by definition. Hence, again the system shows up to be additive as well, additive and homogeneous both. So, this system is also linear. Let us now try to find a non-linear system, a system which defies this definition. Suppose we take y t equals x squared t. Is this system homogeneous? Suppose I apply k x t to the input. K x t, we will call this a x prime t. We apply this at the input. What should I get at the output? I will get x prime squared t. That will be the output. What is x prime squared t? Substituting the value of x prime t, we get that this equals k x t whole squared, which is equal to k squared x squared t, which is equal to k squared y t. So, you see, putting all these multiple steps and together and summarizing our calculation, we find that if you applied k x t to the input, the output you get should have been k y t, which is k x squared t if the system were homogeneous, but what you have got is k squared x squared t. So, the system is not homogeneous. Once homogeneity has failed, it is reasonable to expect in most cases that additivity will fail also, but let us go ahead and prove it. If y 1 t is the result of applying x 1 t to the input, that is, if you apply x 1 t, you should get x 1 squared t as the output, we call that y 1 t. Right, that is just the definition of our system. Call this y 1 t, x 2 t would yield correspondingly x 2 squared t, call this y 2 t. Now, let us see what happens when you apply both the signals simultaneously. You apply both these together. What happens? The output signal, we are told, is the square of the input signal. So, if this is the input signal, the output you get will be the whole thing squared, x 1 t plus x 2 t whole squared, which as we know expands to x 1 squared t plus x 2 squared t plus twice of x 1 t times x 2 t. This on simplification comes to y 1 t, x 1 squared t is after all y 1 t plus y 2 t plus this unfortunate term called 2 x 1 t x 2 t. So, when you applied x 1 t plus x 2 t at the input, you ought to have got only y 1 t plus y 2 t at the output. If this had happened, then we would have said that the system is additive. But apart from these two terms, there is this additional term 2 x 2 t x 1 t, 2 x 1 t x 2 t. This term spoils the additivity of the system. The system is not additive. It is not homogeneous as we have already shown, it is also not additive as we have just shown. So, together the system is not linear. An example of a non-linear system. Let us take another example and see what happens. If x t is taken, stop कीजिए, let us pick a second example. Let the system be given by this equation y t equals mod x t, the absolute value, let us see if this system is linear. The right way to do it, of course, is to first test for homogeneity and then subsequently test for additivity. So, let us start with testing for homogeneity. If y t equals mod x t, then what is the output corresponding to a scaled version of the input? So, instead of x t, let us apply an input like a times x t. suppose this is the input, then the output we should get would be mod A x t, which as we all know is equal to mod A times mod x t. Now, clearly under all circumstances this will not be equal to A times mod x t, which is what it should be if the system is homogeneous. It should be equal to mod A x t. Instead we get mod A times mod x t, and therefore, this system can be considered homogeneous under certain conditions, and the conditions being that A must be greater than equal to 0. So, if A is greater than equal to 0, it is homogeneous. Only if, otherwise it is not, and therefore, all we can say finally is that the system is generally non-homogeneous. Moving on to testing for linearity, let us consider two inputs x 1 t yielding an output y 1 t equal to mod x 1 t, x 2 t yielding an output y 2 t equal to mod x 2 of t. Now, let us see what happens if we apply both these inputs simultaneously. Then the input becomes x 1 t plus x 2 t, and this ought to yield, not what it actually yields, this ought to yield mod x 1 t plus mod x 2 t. This is what is desired. But what happens actually is that we get instead the absolute value of the entire input. So, that actually the combination which we call y t, the overall output for this overall input, will be equal to mod x 1 t plus x 2 t, which certainly is not equal to mod x 1 t plus mod x 2 t, except when both x 1 t and x 2 t happen to be greater than or equal to 0. So, this does not hold in general. So, the system is not additive. We thus have a nonlinear system. The system is not linear. So, this is a second example in our study of linearity. We will now want to develop more rigorous tests for discovering whether a given system is linear or not linear, and this is what we will next proceed to do.